Okay. So the change of base formula we've actually looked at before. So it's like a, b, and x be positive real numbers where a is not 1, b is not, and b is not 1. Then the log of x base b can be converted to a different base as follows. So the log of x base b is going to be the same as the log of x base a divided by the log of b base a. So that's if we wanted to change it to a base of a. Or we can write it as a base of 10. It'll be the log of x divided by the log of b. Or we can do it with the base of e. So that's going to be the natural log of x divided by the natural log of b. So, we worked an example earlier where we had something like log of 25 base 5. And what we did to calculate that, we used a change of base, and we said that's the same as the log of 25 divided by the log of 5. So, this one asks us to compute by changing the common log to a common log and natural log, but I'll leave it as an exercise. And so all it is you do for a, you'll say the log of 25 divided by the log of 4, it should be the exact same as the natural log of 25 divided by the natural log of 4. You put it in your calculator and you get a result. And it's something similar for part B. So in this example 5, we're looking at an example on modeling with a logarithmic function. So we want to find an equation of the form y equals c plus b log n, whose graph contains these 2 points. Okay. So looking at A, okay. So we got 3, 3. So then what I'll do, I'll say 3 equals c plus b times the log 3. The n is like our x in this case, and it's going to be 3. What I'm going to do now, x and y, I'm going to take the other one. Actually, I'm going to try something different. I'm going to solve for b here. Now, if I solve for b, I'll get 3 minus c equals b log 3. Right? So then I divide, and b is going to be equal to 3 minus c divided by the log of 3. Okay? So now if this is my b in the first one, then I can go and plug it into a second equation. So in my second equation, I'm going to have 1 equals c plus, but my b is 3 minus c divided by the log of 3. That's my b times the log of 9 in this case. Okay. But 9, this is the same as 1 equals c plus 3 minus c divided by the log of 3. But 9 is the same as, we're going to say, the log of 3 squared. So now the exponent can go in front of the log, and we'll put it here. And it's the same, use the commutative property of multiplication. And we'll get, so now we have 1 equals c plus 2 parentheses 3 minus c. Then on bottom we have the log of 3, and on the top we have the log of 3. So what do you think happens? This cancels that. So then we have 1 equals c plus 6 minus 2c. So subtract, we'll get negative 5 equals negative c, so then c equals 5. Okay. So then if c is 5, then that means that b is going to be 3 minus 5 divided by the log of 3. It's going to be a negative 2 divided by the log of 3. Okay. So then that means our function is going to take the form y equals c, which is 5, b, which is negative 2 over log 3 times the log of n. So what we could do to verify this is, plug in when x is 3, we should get 3, and when x is 9, we should get 1. Let's actually do that really quickly to confirm. So now if we say 5 minus, now we're going to say 2 divided by the log of 3, there's that. Then we want to say times the log of, we're doing the first one, so it should be 3 then. And our result should be 3. Okay, that checks out. Then I'm just going to call back that same thing, but instead of x being 3, now x is going to be 9. And when x is 9, it should be 1. Okay, so it checks out. Okay, so then this is the result for A. And then it says, if we look at B, we'll see that, It's actually the exact same, but we're just changing the base basically from base 10 to base 8. So notice we have the log of n divided by the log of 3. So then we can do a direct application and we'll get y equals 5 minus 2 log, now the base is going to be 3 of x. So we just changed the n to an x, but what we did was to change the base formula. So exponential growth or decay occurs when a quantity grows or decreases at a rate proportional to its size. So the exponential growth formula is a of t equals a naught e to the kt, and the decay formula is the same except the exponent is negative kt. Where a of t is the amount of the substance or proportion at the time t, a naught is the initial amount, and t is the time. So now we have this half-life formula. So this is actually a really good opportunity for extra credit. So you can actually start with this exponential decay formula here at the top of your screen. And if you start with an amount, say p, and you finish with half of that, meaning you'll finish with half of p, and when you solve for the t, which is time, you'll get this half-life formula. So if you just turn in on box the derivation for the half-life formula, starting with the exponential decay formula and finish with this half-life formula, you turn that into box before the end of the semester, and I can offer some bonus to you. Okay. So we have the half-life formula here. Let's see it in action. So in this example, we have an experiment that has 25 grams of radium decayed to 8.46 grams in 2,500 years. We want to find the half-life to the nearest year. Now, if we try to directly use the half-life formula, we need the rate, but the rate wasn't given to us anywhere in this example. So we might start with exponential decay formula. So we'll say a of t equals a naught e to the negative kt. So then the final amount was 8.46 grams. We started with 2,500 grams. E to the negative, the rate we don't know, and the time is 2,500 years. So that's a negative 2,500 K. Okay, now if we're trying to, wait a minute, we made a mistake somewhere. We started with 25 grams, not 2,500 grams. Okay. So then if we solve for the rate, I'll divide by 25. So we'll get 8.46 divided by 25 equals e to the negative 2,500k. So to get that out of the exponent, can you guess what we do? Take the natural log of both sides. So we'll take the natural log of this, natural log of this. Exponent is going to go in front of the log, and natural log and e cancel, so that because they're inverses of each other. So now we'll have the natural log of 8.46 divided by 25 equals a negative 2,500k. So that means k is going to be 8.46 over 25, taking the log of that all over negative 2,500. Okay? So that's an exact result for k. But then we want the half-life. So the half-life says half-life is natural log of 2 divided by k. So our half-life will be the natural log of 2 divided by this k here. Okay, so let's just put that in the calculator to get our number. So then we're going to say the numerator is going to be the natural log of 2 divided by the denominator. Now first we have the natural log 8.46 divided by 25. Now that's the numerator. Divided by the bottom is a negative 2,500. That closes off the denominator, and then that should close off our parentheses. Okay. So then the half-life ends up being approximately 1,600 years.